Welcome back. In the last video we have seen how to find the inverse Laplace transform, ways to find inverse Laplace transforms. Started with finding using partial fractions, and then we also used convolution theorem to find the inverse Laplace inverse. And the third way to do this is by Heaviside expansion. So, Heaviside expansion theorem tells you that if you have a rational kind of function of s, which is the numerator is degree of the numerator is less than the degree of the denominator, then if they both are polynomial degrees, if it is a rational expression, then you can find you can express the inverse transform just using this. Is also the technique is basically using partial fractions, but without finding the partial fractions, just based on this p by q, which are the polynomials of the numerator and denominator, you can find a Laplace inversion. That is actually Heaviside expansion theorem. Before I do this, we can also see, you can see that Heaviside expansion. Let's first do this, and then we'll see what is generalization. It's not a generalization; it's a kind of sometimes it may work. You may work with series, Heaviside expansion series. Okay. So before I what we have seen is this is the Heaviside expansion theorem. This is the technique. Let me put it as 3. Third way to get the Laplace inversion. If your f bar of s is this, then you have and where p bar s and q bar s are polynomials such that degree of q bar of s is bigger than degree of ps. Let us say the denominator degree is n, and you also assume that the denominator polynomial has distinct roots, then the Laplace inversion is simply you get like this. Okay. So this is also actually similar to finding partial fractions, but without finding the partial fractions, you can just calculating, you can considering p bar and q bar, and you simply get this expression p bar by q bar dash, that is a derivative of q bar, and you replace s by alpha k. These are the roots of this q bar f denominator, q bar of s equal to 0. So let me prove this before I make some more remarks on this way of finding inversion. So you assume that q bar of what is given is q bar of s is basically having n distinct roots. So I can explain, I can write this as so q bar is a polynomial. So some constant times, let us call this a naught times s minus s naught, s minus alpha 1, s minus alpha 2, and so on, s minus alpha n. So you assume like this, then you have f bar of s, which is p bar of s divided by q bar of s. This is, you can express this as a because the degree of ps is smaller than qs, and qs has all simple roots, that is the distinct roots. You can write this using partial fractions. I can write like some k is from 1 to n, simply some constant times a k divided by s minus alpha k. So let us where a k are constants, where a k is a constant. So if you do this, what is p bar of s? If you write this, this implies this will give me p bar of s as q bar of s into this. So you have k is from 1 to n, a k by s minus alpha k times q bar of s here. So this is simply I can write this as k is from 1 to n, a k times q bar of s is this one. This one, if you use here, you s minus alpha k will go, so that you can write s minus alpha 1, s minus alpha 2. Of course, you have a naught here. A naught is a constant which is in the here, times what you are missing is s minus alpha k, you can cancel it. So, you have s minus alpha k minus 1, and then the next term is s minus alpha k plus 1 up to s minus alpha n. This is what you will have as an expression. So, where k is this one. So, this is the summation. Okay. If I substitute p bar of alpha k, this is equal to only when k equal to alpha k, when I substitute s equal to alpha k, s equal to alpha k, only this term when k, k rather I think k is k minus 1, k plus 1. So, okay. So, all those terms will go except one term when k, for that s minus k, s equal to when you put alpha k. So, when you put alpha k, so what is left is a 0, a k, s minus alpha 1, s minus alpha 2 up to s minus alpha k minus 1, s minus sorry s, this is alpha k, this is alpha k, I am placing in the place of s alpha k. So, you have alpha k minus alpha k plus 1 up to alpha k minus alpha n. So, this is non-zero quantity. Okay. And then so only one term. So, that is this general term when I replace s equal to alpha k. If I have s equal to alpha 1, when k equal to 1 we will be having. So, when k equal to 1, so you have so when k equal to 1, when s equal to alpha 1, what you have is, in this case first term will not be there. Okay. So, this is so let us say if s if I use s equal to alpha 1, what exactly your p bar of alpha 1, this is going to be a naught, that first term which you will have, what you will lose is the first term. So, that is a naught times a 1 s minus alpha, that is alpha 1 minus alpha 2 up to alpha minus alpha n. So, except that alpha 1 minus alpha 1, that is 0, that divide with that when k equal to 1, that gets cancelled. This is your first term. So, first term will remain when s equal to alpha 1. When you take s equal to alpha k, only kth term will remain, right. Kth term is this general term. So, that is what is your p bar of alpha k. You differentiate what is your q bar. Q bar, if you differentiate q bar of s, q bar dash of s, that is what is this one, q bar of s, if you do, this is also again you see that k is from 1 to n, a naught times, if you differentiate. So, you have to differentiate first term and keeping everything is as it is. So, if you do that, the only because of s minus alpha 1, s minus alpha 2, s minus alpha n, if you differentiate each term, only thing is a naught is common, that is comes out, and then and you end up n terms, that is s minus alpha 1, s minus alpha 2, what you have is only kth term will go, that is s minus alpha k minus 1 into s minus k alpha k plus 1 up to s minus alpha n. So, this is what is the q bar of s. Again q bar of s alpha, if you replace q bar of s by alpha k, this is going to be what is q bar of alpha k? This, if you put alpha k, s equal to alpha k, s equal to alpha 1, and if I put it is going to be a first term when you have k equal to 1. What you have is there is no alpha minus 1, this term is not there. So, you have s minus alpha 2, this is 2 onwards will be there. So, whatever these are the terms will not be there. Okay. This term will not be there because s minus when k equal to 1 alpha 0. So, there is no such term. So, it is like k equal to 1, when s equal to alpha 1, and what you end, so you end up getting a naught times s alpha 1 minus alpha 2 up to alpha 1 minus alpha n. So, you getting here you get the nth term again here. So, something like s alpha 1 alpha k minus alpha 1, because I am replacing s by alpha k, and you have alpha k minus alpha 2 up to alpha k minus alpha k minus 1 times alpha k minus alpha k plus 1, and then finally alpha k minus alpha n. So, if you compare this this with this, you can easily see that a k is actually equal to p bar of alpha k divided by what is remaining is this q bar dash of alpha k. So, this is true for every k running from 1 to 3 up to n. So, if you go and substitute into this, these are the unknown constants, f bar of s is actually equal to, so you have k is from 1 to n, a k I am replacing with p bar of this constant alpha k divided by q bar dash of alpha k, there is your a k, 1 divided by s minus alpha k. So, from which you can get your this is a finite sum, and I know what is the inverse transform of this. So, you have f of t, that is Laplace inversion of f bar of s, which is a function of t, is equal to this sum k is from 1 to n p bar of alpha k by q bar dash of alpha k times 1 minus, this is going to be e power alpha k t, s minus 1 over s minus alpha k is, whose Laplace inversion is e power alpha k t. So, this is how you get this Heaviside expansion. So, without making partial fractions, if you have a distinct roots, you can easily see that if you have a denominators having distinct roots, you simply get these derivatives and find those roots first of all, and then get these roots, get the derivative and substitute. So, those coefficients are nothing but these, okay, coefficients of this partial fractions you can easily find this way. So, this proof is really not that difficult. Okay. So, this is the Heaviside expansion, this is the way you can get the inversion. And the last video we have seen as a Heaviside expansion when I started. So, if you start with f bar of s, okay, and suppose you have this, and you started with let us say you started with a Maclaurin series. So, you have a Taylor series around 0. So, for t positive you have already this expansion. So, you have a validity, once you say it is a Taylor expansion, it is valid in the neighborhood of 0. So, that means you started with a Taylor series in the neighborhood of 0, that means you have f of t for t positive in the neighborhood of 0, it is well defined. You have for such a function, let us say suppose that it is defined, you have a Taylor series, suppose it is valid for all t positive. You started with this type of Taylor series, Maclaurin, that is called Maclaurin series around 0. Then if you find the Laplace transform for that, you see that is going to be Cn over Sn plus 1 with this summation, this series, because you do the term by term, because this is uniform convergence. This Laplace inversion, Laplace transform is uniform convergent integral. So, you can bring this integral inside the series by after substituting ft as a series, you can bring this integral inside. So, for each of this integral is a Laplace transform of the each term here. So, that makes it Laplace transform of this full series is this one. So, that implies once you have this, by inspection you can see if you have a series like this, you can immediately write that you have a series, you have Laplace inversion is this function. Okay. So, we can use this, this is a kind of because we are seeing that this is a Heaviside expansion theorem. So, here of course, we have only finitely many terms. Sometimes this is another this is not a Heaviside function, but it is a kind of you have a series form, you can do term by term Laplace inversion. So, sometimes it may so happens that you can easily work out if you are having this Heaviside expansion, for example this one. If you have some it need not be polynomial, if Ps f bar of s is p bar of s by q bar of s. For some functions q bar of s having infinitely many distinct roots, for example, then you can get this Laplace inversion of f bar of s not by this Heaviside expansion theorem. So, you can easily see the same way you can calculate, which is from k is from 1 to infinity, the same expression will be valid. This is q dash of alpha k times e power alpha k t. So, you see that as though you applied this Heaviside expansion theorem, even if you have f p bar of f q bar of s, q bar of s is having infinitely many roots, infinite zeros. Okay. Even if you have infinite zeros, what you have is as a polynomial, if you have infinitely distinct roots, you can still get this kind of distinct roots, infinite distinct roots, distinct zeros. You can show that it is actually this by a general form of general way of getting the Laplace inversion, that is by actual definition inverse integral, inverse transform of the inverse Laplace transform of f bar of s, that is by contour integration over 1 by 2 pi I times integral over c minus I infinity to c plus I infinity, the definition the f bar of s into e power s t d s, that is complex integral we may have to evaluate, and then using the contour integration technique you can actually see that you can get the inversion that we will see in the next way of finding the Laplace inversion. Using that you see that you can see that the term by term you can easily, almost like a Heaviside expansion, you can get it. This is a finite sum, you can easily prove this Heaviside expansion theorem, but if you actually use the basic definition of the inversion by contour integration technique, sometimes if you have f bar of s is with p bar by q bar of s, and q bar of s is having infinitely distinct root zeros, the inversion of this Laplace transform is you can simply do the term by term thing with work with the same way like you have done for Heaviside expansion theorem. Okay. So, that we will see when you do the complex integration technique. Okay. So, let us and this thing will help you. This is like a straightforward way. If you start with f of t, you end up getting the Laplace transform as this. So, your Laplace inversion is only this one. Okay. So, this way it is well defined for t positive, so that you can see you have for t positive for such class of functions you can easily see that if you have expansion, and you can at least see that you have some kind of theorems like if your f of t as t goes to 0 is if what is this one, as s goes to, what is the limit of f bar of s as s goes to infinity. So, you will know what is in terms of limit of f of t as t goes to infinity. So, these two things are can be related maybe with s power s into this. Okay. These are some so kind of asymptotic analysis, these are useful. So, that we will see when it comes, we will explain this. Okay. So, this part as such for such class of functions f of t, if you have a series like this, and you can easily see that you can inversion will be like this, provided this series is convergent. This series is a kind of convergence. If your right hand side is convergent series and you start with these Cn's, such Cn's, if you have this kind of f bar of s, you can get the Laplace inversion in this form, provided this is the function you started with is convergent integral for all t positive. Okay. So, this is actually this is digress, this is not relevant to this kind of Heaviside expansion. In any case, this is the third way of finding the inverse transform, that is by Heaviside expansion, which you the same way you can work out for in general even if p bar q bar are not polynomials, but some other functions with infinitely distinct zeros, you still get similar kind of expression that we will prove this. You can actually show that by we will not show, but you can show for with some example using contour integration technique. You can see that these constants are nothing but the residues of roots that contributes these numbers. Okay. So, this is the same form as in the Heaviside expansion theorem, which is also which you can use even if p bar and q bar are not polynomials. Okay. We will do some examples. So, let me do some example using this Heaviside expansion. So, one is how do you find this inversion with simple partial fractions s square minus 3s plus 2. So, this is equal to, so what is your p bar of s if you actually consider, that is s, q bar of s is a second degree polynomial s square minus 3s plus 2, this is s minus 2 and s minus 1. Okay. So, this Laplace inversion of p bar of s by q bar of s is exactly what you have. So, this is L inversion of so this we already know that this is sigma. So, what you have, the first term is you have a summation, that is you have only two terms s minus 1. So, you have 1 over L inversion of 1 over s minus 1 with a1 plus a2 divided by s minus 2. So, without finding these partial fractions, I know what is exactly a1 is. A1 is actually p bar of alpha 1. So, let us use which is 1 divided by q bar dash at 1. Okay. That is exactly your number a1. So, similarly a2 is p bar at 2 divided by q bar dash at 2. So, if you calculate this, p bar of 1 is, which is 1. So, simply 1, s p bar of s is s. So, it is 1 divided by q derivative is q bar dash of s is 2s minus 3. When you put s equal to 1, that is going to be minus 1. So, you have minus 1 here. So, you have L inverse of minus 1 by s minus 1, and here this will be 2 divided by 2 into 2, 4 minus 3, that is 1. So, you have 2. So, you have plus 2 divided by s minus 2. So, you have minus e power t and then plus 2 times e power minus 2t minus 2t. This is what is the Laplace inversion. Okay. So, I just use directly this expression. So, you have to calculate its derivative and you have to look at the alpha 1 is 1, alpha 2 is 2. Okay. So, this coefficient of a1 is the coefficient of s minus 1, then you have to choose a1 as p bar of alpha 1, that is 1. Okay. This corresponding to this 1. If you use a2 whatever, say I need not call a1 here. So, I can write a by 1 by s minus 2, 1 by s minus 1. Those coefficients, corresponding coefficients, you have to consider this p and q dash values at that value s minus whatever that root. Okay. So, this is how you find given any polynomial by polynomial, if you have a distinct roots in the denominator, you can just get the Laplace inversion by this way. I will try to give you some I will try to see what is some example where this Heaviside expansion has so happened that it works here. It works because it is not by this theorem. I am just giving you some example where p and q are not polynomials, but something else I give you, but I use this expression because of assuming that this theorem is valid. Okay. Even if you have if you have distinct roots, f bar is having like this, f p bar by q bar is having infinitely many distinct roots, then this Laplace inversion is this. It's this I am using directly this one. This is proof by contour integration. Okay. A definition of inverse transform, inverse Laplace transform as a contour integration, as a contour integral, that we will see as a way to get the Laplace inversion in the next as a part of 4. This is third, which is using Heaviside, is only for finite sums. Okay, this is only for finite sums is valid. If q bar is having like this, and if you have only distinctly many, only finitely many zeros, you can, this is works. But this also happens to work the same way like it works for Heaviside expansion, but the proof is not, because the proof is valid for you can prove this if you consider this as p by q, where q is having infinitely many roots, distinct roots, then this is true. Not this way, but basic definition of contour inverse contour integration, inverse Laplace transform as a contour integration, that contour integral over that actually integral is 1 by 2 pi times c minus I infinity to c plus I infinity. This is the contour integration. Using contour integration you can evaluate this as f bar of s e power st ds. This if you calculate, if you having a distinct roots, infinitely many distinct roots, whatever you have, and you can see that this is actually you see that this integral value is 2 pi I, is 2 pi I goes 2 pi times all the residues at the poles, residues at poles, those poles are these roots. Okay, those poles residues actually you will see that this one into. So, if when you calculate this residue, it happens that this comes because of e power s, poles are, those poles are alpha k, e power alpha k times t, f bar of s, you will see that residue is actually this part, simple poles. At simple poles the residue value is this. So, that is because of this inverse integral, inverse transform definition, you get this kind of form which you can use for some examples, but that is looks like a version of Heaviside expansion, generalization of Heaviside expansion theorem, but the proof, the whatever that we can prove, we cannot prove the way, this is not the proof for that. Okay, the proof that is given for the Heaviside expansion theorem is not a proof for this generalization whatever you are doing for the series. Okay. So, but in any case let me give you an example, and then anyway I will go to give the last way, how general way how to find Laplace inversion. So, let me give you this example. If I give you if I choose alpha as root s by a, okay, then what is the Laplace inversion of cos hyperbolic alpha x divided by s times cos hyperbolic alpha l for some x and l. Okay, x and l are l belongs to real numbers, let us say. Okay, where this is. Then find this Laplace inversion. So, what I do is how do I, you can easily see that this for this example, if you actually see what is my p bar or q bar, if you write that way, p bar of s is cos hyperbolic alpha x, alpha is root s by a, okay, root s by a into x. Q bar of s is s times cos hyperbolic root s by a times l. And you see that cos hyperbolic, this has q bar of s has all the roots, these are the roots, 0 is the one root. So, let us call this s alpha 1. So, I am using alpha here. So, let me call those roots as s1 as 0. So, let me call this s0 is 0 because of this s into this cos hyperbolic s root s by a equal to l. So, that is cos hyperbolic x equal to 0 when you have this roots of this are what are the roots of these roots of, what are these roots of cos hyperbolic s by a l equal to 0. Cos hyperbolic root s by l is root s by a times l equal to if you use cos hyperbolic, you see that cos hyperbolic I times k plus half, any k plus half, that means 2k plus 1 pi 2k plus 1. So, that is odd 2k plus 1 by 2 times pi. With this is going to be cos 2k plus 1 by 2 by pi. So, that is cos that is actually. So, these are cos things that which are 0. Okay. So, that is k equal to 0. If I take k equal to 0, it is going to be pi by 2 cos pi by 2, that is 0. Cos k equal to 1 is 3 pi by 2. Okay. 3 pi by 2, 5 pi by 2 and so on. You can get like this. So, root of s by a l, if I choose like 2k plus 1 pi by 2 and k is from 0 to 0, 1, 2 and so on, and I know that this value is equal to 0. So, that makes it s equal to I square, that is minus if I square both sides, you see that minus 2k plus 1 whole square pi square by 4 times a square. So, that is a, because the root a, when you square it is a, divided by l square. So, this is what exactly your sk. So, for all these sk's, k is from 0, 1, 2, 3 onwards, for which this is q bar of s is 0. Okay. So, these are the roots. Sk is minus 2k plus 1 whole square pi square a by l square 4 l square. So, these are distinct, these are all distinct negative roots. Clearly, they are all negative side, they are all, because they are negative roots, as you see, as you will see in the next technique to find the Laplace inversion, which is basically using the Laplace actual inversion to find the, using the contour integration technique to find, using the Bromwich contour, general way of finding the Laplace inversion. You will see that these things, if you apply, these things will contribute as a residues at these poles. Okay. So, we will see that in any case here, if you simply think that this is true, using the proof is by technique of this contour integration, and when you see that this is going to be same as, this is on the similar lines to the Heaviside expansion theorem. If it is valid, you just see that it is going to be p bar. If you actually see that q bar and q bar is this, these are the roots. Now, what you do is, as though the theorem is valid, you calculate p bar at sk divided by q bar dash at sk. If you calculate, okay, what is q bar dash? If you actually see, q bar dash of s is cos hyperbolic root s by a l plus s times sin hyperbolic root s by a into l times l by root a 1 by 2 root s. Okay, that is what is the derivative. So, this root s goes, so you have this. So, this is exactly what you have as a q bar of s. So, now calculate q bar at sk, you put it here in this and you substitute here. So, if you substitute here, I am just writing directly, you can work out, you will see that you will end up getting. So, for each k, so this you calculate for each k is from 0, 1, 2, 3 onwards. If you actually calculate, so what you see is, so what you have is this times, once you calculate these, all these things, calculate, now you know what is s case and you know what is q bar of s and q bar of s. Q bar of s is this, p bar of s is this, q bar of s is this, q dash is this one. You calculate and you calculate these terms first, and then what you see is L inversion of cos hyperbolic alpha x divided by s times cos hyperbolic alpha L. This is, you can, as though you can write it, you can get the partial fractions for each of this, you try to write L inversion of this p as the partial fractions, this number is this whatever you calculated pk by q bar dash of sk, of course with summation k is from 0 to infinity because you have such that many number into 1 over s minus sk. Okay. So, this is equal to, so L inversion for this as though you can apply this inversion as though you can take this Laplace inversion as though it is a linear operator, though it is not we are only doing formally here. You take this inversion inside this summation, you have this k is from 0 to infinity p bar of sk by q bar dash of sk times L inversion of this is a constant. So, 1 over 1 by s minus sk. This inversion is we know that e power skt. So, this is actually questionable, we do not know whether we can take this inversion inside this infinite sum, but as such. So, we are not using this the proof is we are not using that, we are not saying that we can take this L inversion inside, but when you actually using this principle which we will do later on as a fourth way of getting the inversion, you see that this is always true if you have q bar of s is having infinitely distinct roots. Okay. For this is the example for which this is true. So, these are the residues, these coefficients as the residues. So, that way once you have that residues, L inversion as a residues, if when you calculate you come naturally like this. The same expression you are getting it here by just formally I am allowing this L inverse going inside this infinite sum, you get the same expression. So, it looks like Heaviside expansion theorem, but it is questionable. Okay. But actually by some other means, but the general way of finding the Laplace inversion you can find this, and finally you end up seeing that this is going to be some kind of for k equal to 0 you end up getting 1, and you see the other terms are like no, not 1. So, let me not write this. Okay. As such I will leave it here, let us not do any calculations here. Okay. So, if alpha is this if sk's are the roots, s0 is one root and k is from 0 onwards, k is from 0 onwards if you have roots. So, let me call this s minus 1. So, you have s minus 1 and here sk is from k is from 0 onwards. So, you have k is from minus 1 onwards. Okay. K minus 1 is s minus 1, you can write this, s minus 1 is 0, okay, 1 over s. So, if you do like that, so formally you have k minus 1 from minus 1 to infinity, you have this expression that is same as, that looks like you have formally if you apply this Heaviside expansion theorem, this is what you get. But actually if you use the general way of finding, that I am going to do next, general way of finding the Laplace inversion using the contour integration technique, if you do, you get this expression naturally. Okay. So, that is the reason I give you this expression. So, let us use the next way of finding the Laplace transform, inverse Laplace transform, Laplace inversion for a general function f bar of s. Okay. So, how do I do this? If you have a rational function, it is with polynomial by polynomial, you can do partial fractions. If it is a product of two Laplace transform, you can use a convolution. If it is a kind of again like polynomial by polynomial with the distinct roots, you can use the Heaviside expansion theorem. And also, yeah, these are the three types you have seen so far, and the fourth type is a general Laplace inversion for a general function. Even in the three cases are you can use it here. See, all the three cases are three ways of finding the Laplace inversion. They are all ad hoc methods, all the three which you have seen. This is the general method. Given f of s, f bar of s, given f of s, if it is a Laplace transform, f bar of f of t is the inverse function is 1 by 2 pi times, this is c minus I infinity to c plus I infinity, f bar of s e power st ds, where c is bigger than a with a being A being the with A being the order of exponential function f of t, exponential order rather being the exponential order of the function f of t. So, if you have this is what we have defined, that is how we have defined the Laplace inversion. So, I can directly find this Laplace inversion of f bar of s, that is as a function of t, which is function of t as this 2 pi I times integral c minus I infinity to c plus I infinity f bar of s e power s t dt ds. So, how do I evaluate this in general? So, you have a complex integration, you need complex integration, that I think I will take 1 or 2 hours to explain how we do this integration in the complex variable. So, let me use this x y variable, s is this s is actually x plus I y, s is a complex variable. How do I do this? Actually this is your c, beyond which this is having exponential order, this is actually going to 0 at as s goes to infinity. This is valid, okay, as valid as s goes to infinity. In the complex plane, infinity means in any all directions, if it goes to infinity, this goes to infinity as x, suppose y equal to 0, x goes to infinity, that is also infinity. Suppose y equal to 0, x goes to minus infinity, that is also infinity. So, in a complex plane, as you go in the extremes, that is actually called infinity, all are same, minus infinity plus infinity, there is no distinction. This is infinity, means it is a imaginary quantity, it is there is nothing like, actually there is nothing like infinite thing, that is a notion which is not something which is not finite, okay. So, in the complex plane you can go in all directions. So, in the real line you can go to 2 directions, that is negative side and positive side, that is why you are making a distinction between those 2 extremes, minus infinity and plus infinity. But in the complex plane you can which is not finite, which is not a finite complex number, means you can go to in all directions. That is the reason we the notation wise we put it as 1 infinity, okay. So, minus infinity plus infinity any infinity, infinity plus I plus some constant times I, they are all same as infinity, okay, which is not finite in the complex plane. So, if you do that, this function is having, so what I do is you try to take this, you make a circle out of this like this, you make a circle as a contour. So, this is called Bromwich contour. So, you can do this Bromwich contour. By doing this, if I call this gamma as this plus this, and you have this is your radius of this circle, this is r, as r goes to infinity, this covers entirely this side, all the poles which are inside this side, which are here this side, whatever all the poles as how do I put it, real part of or s is real part of s less than c side, this is the imaginary, okay. This is this side, left side, or this side of the plane, this is your line, left side of this line, all the poles will be inside this contour gamma. So, there is a contour integration, there is a residue Cauchy residue theorem that tells you that contour integration over this plus this is equal to 2 pi I times, okay, that means this 2 pi I times that integral over gamma, let us call this f bar of s e power s t as your complex valued function, ds is actually equal to 2 pi I times all the residues, sum of all residues. So, 1 by 2 pi if you bring it here, so you have to calculate this integral over this is actually your integral. So, your actual integral plus over this integral, because of this nature of this function, the integral over this contour will be vanishing. So, that way what remains on the left hand side is what you need, that is the integral over not f bar of s, integral over c minus I infinity to c plus I infinity will be a summation of all the residues. Now, if you have infinitely many roots as in this example, if you consider this as a function, as a complex valued function, cos hyperbolic alpha x by s into cos hyperbolic alpha l, where alpha is root s by l, that involves s. Okay. So, using that you see that all the poles will be inside, all the poles on the negative x axis. As you see, the roots of that q bar of s are all like this, are all negative sign of, so they are all on the negative side of the x axis, they are all here. Okay. Everything is here. So, when you expand as r goes to infinity, you see that this is going to be 2 pi times residue as at that at those points k equal to 0 to infinity. So, s equal to 0 is also here. So, this one and all the negative signs are here. So, you see that in that way, if you use this principle, this theorem or rather this contour integration technique, you see that you end up getting sum of all the residues. That is exactly that is exactly how you calculate this f of t as inverse Laplace transform of f bar of s. So, this is actually equal to 2 pi times, so 2 pi goes, you see that sum of all residues of f bar of s e power s t, this function is a function of a, and s belongs to this complex plane, the real part of for at all residues, at all poles, or rather let me call it s equal to sk, where sk's are poles. So, k is from, if you have infinitely many, k is from 0 to infinity, call this. So, this is how you calculate. So, you should know how to find residues of a complex valued function, okay, defined over a complex plane. So, this is what I will explain in the next few videos, how to find the how to make integration in the complex variable. We start with what is actually integration in the real line. So, over an integral, what is the meaning of real valued function, what is the integral of it, and then we will move on getting what is the integral over a real on the real line, what is the complex valued function integral, and then we will go to integral over a complex plane, over a line in the complex plane, what is the integration of a complex valued function. So, these things we will try to make a distinction, and finally we end up seeing finally what you see is integral over f of z is a complex valued function, that is u of x y plus I times v of x y. Okay, it is a complex, that is a complex valued function of complex plane, x y belongs to the plane, and this is over some curve gamma. So, let me call this gamma here. If I put gamma, this as your f of z dz. So, this is the integral you are interested. So, this you can easily calculate if you can parameterize this gamma. Okay. Gamma, if you call this like this in your plane, you should know how to parameterize as gamma of t belongs to some real line. So, real interval, let us call this AB. So, if you take this piece, gamma of A is actually this point, as you move along t from A to B, you move along, gamma t moves along from this point to this point on the curve. So, integral over that curve means what? That is exactly we will see. Okay. And then, so those are such integrals, these are the integrals, those are such integrals, what you have, what you need. This is such one such integral. So, how do I find this? Using contour residue, Cauchy residue theorem. So, this in order to get this theorem, so we will briefly explain what is the integration, and then finally briefly about those results on in the complex variables, how to find the contour integration technique. I will try to spend 1 or 2 hours on this, and then come back to this general way of finding the Laplace inversion of a given function f bar of s, and then we will do some example how to find the inversion. So, this is the general way of finding the inversion. If you do not know, how do you, if you do not know already from the list, if you do not know, if you cannot use the list of Laplace transform and its inversions, this is the way to find the elementary functions, you know. If you have a complicated function, so there is no other way to use this general inversion formula to find the Laplace inversion, which is a function of t. But then this formula is actually contour integration, it is an integral, complex valued integral. So, complex integration over some contour in the complex plane of a complex valued function. So, you need to know how to find a contour integration to evaluate this. So, that is what exactly we evaluate using this Bromwich contour method, and so that you see that is all residues, that is going to be that is going to be sum of all the residues. Okay. So, we will explain how these things in the complex variables, how do you find this integration complex variable technique, residue technique, residue calculus technique in the complex integration. We will spend 1 or 2 hours in this and then come back to this Laplace inversion using this contour integration technique. Thank you very much. We will see in the next few videos all such things. Thank you.